This is the first of two videos on the pigeonhole principle. We're just going to look at a basic form, or some people call it the naive form of the pigeonhole principle. And the pigeonhole principle says if you've got n holes and you have more than n objects, say n plus 1 or more, then there's a hole that contains at least 2 objects. So let's see if we can use that concept. Hopefully this next example might further elaborate on this and explain it a bit. You have 13 red, 10 blue and 8 green socks. How many socks are needed to be selected at random to ensure that you have a matching pair? So what I'm going to do is create a box or a hole. Red, R for red, B for blue, and G for green. And see what we have to do. As you're picking out each of these socks from wherever they come from, maybe a big clothes basket, when you start putting one in, even if you have the worst case scenario, it's going to be on the 4th time. So yeah, let's look at the worst case scenario. Alright, so let's say first one's red and then you get a green one, put it in that hole, then you get a blue one. Alright, there's 3, I still don't have a matching pair, get another one out. Now it's got to be one of red, green or blue. So you'll end up putting 2 objects. Worst case scenario on the 4th time. So that with the 4th one you will get a matching pair of some color. So the answer is 4 socks need to be selected. Next example, show that for any 5 points chosen inside a 2 by 2 square, at least 2 of them will be no more than square root of 2 apart. What this actually means is that if you've got something like this, and it's a 2 by 2 square, so it's 2 along there and 2 along there, and we've got 5 points in them, so that would mean that excluding the lines, which is a bit of a grey area. So I mean, and technically a line really has no width anyway if it's a true line, so we're going to neglect the lines themselves. If we have 5 points, we are going to consider the perimeter as part of the square, of course. And if you have 5 points, well, you can put them anywhere in square 1 and anywhere in square 2, have to put another one square 3 and square 4. In other words, if we're trying to break this square root of 2 apart, let's put them as far apart as possible. Well, these 4 are as far apart as possible, but we've got to put a 5th one somewhere. Alright, now we're ignoring the lines, as I said before, because they aren't really there. Okay, that's just there to show. And basically, wherever you go, let's put it in. It's got to go into one of the squares, 1, 2, 3 or 4. So here, this is as far apart from all of them, in fact. So we've got let me get a color. We've got a 1 there and a 1 there, and no matter which way you go, you've got this diagonal as the distance. That's the furthest apart. So that answers the no more than root 2 apart, and you're basically using Pythagoras' theorem. You got 1 squared plus 1 squared square root, and that's square root of 2. And as I said, that's the worst case scenario. That's as far apart as we can, so that answers the question. Okay, how many students do you need in a school to guarantee that there are at least 2 students who have the same first 2 initials? So at least 2 students have the same first 2 initials. So we've got 26 letters in the alphabet, and we've got the first two initials, so 26 for the first and 26 for the second. So that's an AND, which means multiply, multiplication principle. And calculating that, we get 676. Now at this point I'd like to show you a different interpretation of the pigeonhole principle, I suppose. Makes just as much sense. If more than n objects are distributed into n boxes, then at least one box must have at least two objects. There's lots of at least there, isn't there? It feels like it anyway. If more than a certain number of objects is placed into that number of boxes, then at least one box must have at least two objects. If you pause and think about that, it does make sense. Now we've got 676. That would be our value for n, because we've got 676 different items that could go in the boxes. The minimum number of students we would need would be higher than 676, so the minimum number would be 677 students. At least that we would have to choose to guarantee two students would have the same first two initials. Lastly, we have 7 football teams played 22 games of football. Show that some pair of teams play each other at least twice. This one is classic pigeonhole principle. So there are 7C2 ways, which is 21 ways that two teams can play each other based on a total of 7 teams. So 7 teams choosing 2 at a time. So if we had 22, by the pigeonhole principle, we would have at least a pair of teams play each other twice, because you're filling essentially the boxes. So once you get to 21, you're guaranteed that there's a team there that's going to play each other twice. Keep smiling.